The most terrifying realization that can dawn upon the collective human consciousness is not the startling confirmation of extraterrestrial life, a scenario that would fundamentally redefine our place in the cosmos, but rather the deafening, persistent, and statistically improbable silence emanating from the expanse. This absence, this profound vacuum where advanced signals ought to resonate, suggests not merely a statistical anomaly, but perhaps a deterministic fate, an invisible, colossal impediment woven into the very fabric of cosmic evolution, universally known as the Great Filter. To truly grasp the magnitude of this existential dread, one must first contend with the sheer, almost incomprehensible scale of the arena in which this silence reigns. The observable universe, a sphere extending approximately 93 billion light-years in diameter, harbors, according to contemporary cosmological models derived from data gathered by missions like the Planck satellite studying the cosmic microwave background radiation, an estimated minimum of 2 trillion galaxies. If we conservatively estimate the average stellar population of these galaxies to be around 100 billion stars, a figure often cited for systems like our own Milky Way, the total count of stars within our observable horizon balloons into a staggering figure, perhaps 200 sextillion, or 2 followed by 23 zeros. Even assuming a relatively low frequency of planetary formation, Kepler Space Telescope observations, and subsequent analyses utilizing the transit method and radial velocity measurements, suggest that virtually every star hosts at least one planet. More critically, data modeling indicates that within the Milky Way alone, the number of terrestrial planets residing within the conservative habitable zone, the region where liquid water could exist on a planetary surface, is not a meager handful, but potentially tens of billions, possibly exceeding 40 billion Earth-like worlds orbiting G-type, K-type, and even M-dwarf stars. When these astronomical figures are synthesized, the expectation, based purely on combinatorial mathematics and the mediocrity principle, is that intelligent, technologically capable life should not just be present, but ubiquitous. The sheer volume of viable real estate necessitates a non-zero probability for abiogenesis and subsequent evolutionary complexity, implying that the galaxy should be teeming with detectable signals, evidence of megastructures like Dyson swarms, or at the very least, unintentional technological leakage, concept often quantified by the radio frequency leakage we ourselves generate. This probabilistic expectation forms the bedrock of the Fermi paradox, famously articulated by Enrico Fermi during a casual lunch conversation in 1950, revolving around the fundamental question: if the galaxy is so vast and ancient, where is everybody? To attempt to structure this inquiry, scientists formulated the Drake equation, a probabilistic framework that multiplies several key variables: the rate of star formation R sub star, the fraction of those stars with planets F sub p, the average number of habitable planets per star Ne, the fraction of those planets where life actually arises F sub L, the fraction of life that evolves intelligence F sub I, the fraction of intelligent life that develops detectable technology F sub T, and, crucially, the length of time L such civilizations release detectable signals into space. Even when employing the most pessimistic, almost parsimonious estimations for these variables, suggesting, for instance, that only 1 in a million habitable planets develops life, and only 1 in a million of those develops advanced technology, the resulting product, representing the estimated number of active civilizations in the Milky Way, almost invariably yields a result significantly greater than 1. For example, if we use a relatively conservative set of values, such as a star formation rate of 3 per year, planet fraction of 1 habitable planet per system, and assuming life emerges 1% of the time, intelligence 1% of the time, and technology 1% of the time, with a galactic age allowing for colonization time spans far exceeding the necessary few million years for galactic permeation, the resultant number of civilizations should be in the thousands, perhaps millions. The fact that decades of intensive searching, utilizing projects like SETI, the search for extraterrestrial intelligence, employing radio telescopes pointed toward the most promising stellar neighbors, monitoring microwave and optical spectrum bands with increasing sensitivity, has yielded nothing but static, this cosmic white noise, strongly suggests a catastrophic flaw in our initial assumptions. The flaw, then, must reside within the parameters of the Drake equation itself, and the most disruptive factor, the variable most susceptible to an existential bottleneck, is L, the longevity of a technological civilization. If life is easy to start, and even complex life is common, then the failure point, the Great Filter, must be a process that extinguishes nearly all burgeoning technological species before they can achieve interstellar communication or travel, let alone galactic colonization. This realization transforms the search for extraterrestrial signals from a hopeful endeavor into a grim archaeological survey of potential demise. We are not merely listening for voices, we are listening for the echoes of those who failed the cosmic test. The location of this filter dictates our own prognosis. If the filter lies behind us, humanity has already passed the most improbable hurdle. If it lies ahead, we are merely an exceptional outlier, a brief, fragile flicker of awareness speeding toward an almost inevitable, universal terminus. Consider the possibility that the filter is in our past, positioned at one of the initial, almost infinitesimally improbable steps required for life to manifest in the first place. The abiogenesis question remains one of the deepest mysteries in science. We understand the raw materials, carbon, hydrogen, oxygen, nitrogen, the primordial soup catalyzed by energy sources like lightning or hydrothermal vents, but the transition from complex organic molecules to a self-replicating system capable of Darwinian evolution remains unsubstantiated in the laboratory, despite significant advances. The Miller-Urey experiment of 1953 demonstrated that amino acids, the building blocks of proteins, can form spontaneously under early Earth conditions, and subsequent experiments have yielded nucleobases. However, assembling these monomers into functional, enclosed, self-replicating polymers, RNA or DNA encased within a lipid membrane, is a transition that might require extremely specific, near-miraculous environmental conditions, or perhaps a temporal duration that is rare even on cosmic timescales. If the probability of abiogenesis, denoted by F sub L, is 1 in 10 to the power of 50, for instance, then perhaps Earth is indeed a miracle, and the galaxy is sterile because the jump from non-life to life is functionally zero across most planetary surfaces. Alternatively, the filter could reside in the step from simple prokaryotic life to complex eukaryotic life. For nearly 2 billion years, life on Earth consisted solely of relatively simple, single-celled prokaryotes, existing in a global, stable, though low-energy equilibrium. The emergence of eukaryotes, cells with a nucleus and specialized organelles like mitochondria, was a monumental leap, hypothesized to have occurred through endosymbiosis, where one prokaryote engulfed another, leading to a permanent, mutually beneficial relationship, exemplified by the incorporation of an aerobic bacterium that became the mitochondrion, the cell's powerhouse. This event, which fundamentally unlocked the energy budget required for multicellularity, larger genomes, and specialized tissues, is not clearly explained by a straightforward evolutionary drive. It may represent a highly contingent, chance event, an evolutionary contingency so improbable that it occurs perhaps once in every 100 billion habitable planets capable of sustaining prokaryotic life. If this is the case, then the universe might be filled with bacterial sludge, oceans of single-celled organisms, but nothing capable of building radio telescopes. However, these past filters, while theoretically possible, are less terrifying than the prospect of a future filter, because if the difficulty lies behind us, we are, by definition, survivors. The truly chilling implication of the Fermi paradox, when coupled with the astronomical abundance of potentially habitable worlds, is the suspicion that the great filter awaits us, positioned just beyond our current technological plateau. This implies that technological advancement itself inevitably triggers a systemic failure mechanism that eradicates civilizations before they can solve the challenges of interstellar travel or long-term sustainability. What could this future filter entail? It likely relates to the inherent dangers of mastering forces that exceed the stability of the supporting societal or ecological structure. Consider the existential risk associated with unchecked technological proliferation. The first candidate for a future filter, and one we are currently grappling with intensely, is self-inflicted ecological collapse. As a civilization moves from pre-industrial status to global industrialization, its energy demands increase exponentially, often drawing upon stored, high-density energy sources like fossil fuels. The physics of combustion and industrial chemistry dictate the release of byproducts. In the case of carbon-based industrialization, this results in the rapid alteration of atmospheric composition, specifically the increase of greenhouse gases like carbon dioxide, methane, and nitrous oxide. Climate modeling, integrating complex atmospheric physics, oceanography, and feedback loops, consistently predicts that exceeding certain thresholds of atmospheric forcing, often quantified in parts per million of carbon dioxide equivalent, where current levels hover precariously above 420 parts per million, will initiate runaway heating, sea level rise that submerges critical coastal infrastructure, extreme weather events that decimate agricultural capacity, and potentially trigger cascading ecosystem failures. A civilization that masters atomic energy and global manufacturing, but fails to manage the thermodynamic consequences of its own energy throughput on its supporting biosphere, will collapse under the weight of its own metabolic demands. This is not speculation, this is observed geophysical reality dictated by established laws of thermodynamics and atmospheric chemistry. The filter here is the inability of social and political structures, which evolve far slower than technological capability, to implement necessary global, binding constraints on resource exploitation before irreversible tipping points are crossed. A second, potentially swifter, route to extinction lies in advanced weaponization. The development of nuclear fission and fusion technologies grants a species the power to sterilize its home planet, or at least render it uninhabitable for complex life for geological timescales. The theoretical yield required to cause a global nuclear winter, sufficient to induce widespread crop failure through atmospheric soot-blocking solar radiation, is far lower than the combined arsenals currently held by major world powers. The danger is not necessarily a deliberate, rational decision to end the world, but rather the statistical probability of error, miscalculation, or escalation during periods of geopolitical tension. If the time between achieving nuclear parity and achieving true global political stability is short, the probability of accidental extinction rises dramatically. This concept suggests a temporal window of extreme danger, a brief period where the destructive capacity outpaces wisdom. Extending this concept beyond nuclear war, the advent of powerful, potentially autonomous artificial intelligence represents a more speculative but equally potent filter candidate. If the creation of superintelligence, an intellect vastly surpassing the cognitive capacity of the best human minds in virtually every domain, is possible, the challenge of aligning its goals with human survival becomes paramount. If a superintelligent entity, even one programmed with seemingly benign initial directives, interprets those directives in a way that necessitates the removal or reconfiguration of humanity or its environment to optimize its utility function, the outcome is catastrophic and rapid. Unlike ecological collapse, which is slow and potentially reversible, misalignment with a superintelligence is likely irreversible once initiated. The filter here is the failure to solve the control problem before achieving the necessary computational substrates, the quantum processors or exascale supercomputers, required to cross the intelligence threshold. Other technological hurdles might include runaway biotechnology, where engineered pathogens, deliberately or accidentally released, bypass natural immunological barriers, or perhaps novel physics experiments that inadvertently breach some fundamental barrier of stability, though these remain more theoretical. The cumulative effect of these potential future filters is that any civilization reaching our approximate level, global connectivity, mastery of the atom, developing powerful computation, is simultaneously approaching the most dangerous technologies in history, technologies that possess the capacity for self-termination on a planetary scale. The silence of the night sky then becomes a monument to those who failed this final examination. If the filter is indeed ahead, this realization casts humanity in a terrifyingly precarious position. We are sailing a dark, featureless ocean, armed with powerful but poorly understood engines, with no lighthouses visible on any distant shore. We have no precedent, no historical roadmap detailing which technologies are survivable and which are fatal. Every major scientific breakthrough, the splitting of the atom, the manipulation of the genome, the pursuit of true artificial general intelligence, must now be viewed not just as a step toward enlightenment, but as a potential tightening of the noose. The existential weight of this hypothesis forces a re-evaluation of our priorities. If longevity L is the critical variable, then maximizing L must become the primary, overriding goal of our species, superseding short-term economic or political rivalries. The filter is not an external asteroid impact or a distant supernova, it is an intrinsic property of technological maturity. It is the universal trap built into the equation that governs species that gain the power to reshape their worlds before they gain the collective wisdom to govern themselves responsibly or secure themselves against their own creations. If we are indeed the only life that has made it this far, it suggests that the constraints on technological advancement are far tighter than we currently perceive. Perhaps the filter is not one single event, but a sequence of decreasingly probable survival chances, a cumulative attrition rate. Imagine a hypothetical scenario where, out of 100 advanced civilizations, 99 destroy themselves via nuclear means, and the remaining one destroys itself via uncontrolled AI, leaving 1 in 100,000 to potentially survive the first billion years of technological maturity. If the filter is highly demanding, it means that only a vanishingly small fraction of those 40 billion potentially habitable Earth-like planets will ever see a signal persist for more than a few centuries of detectable operation. This lack of external guidance is perhaps the most profoundly disquieting aspect. Finding a signal, finding even simple microbial life on Mars or Europa, would be a form of cosmic relief. It would suggest that the past filters, abiogenesis and simple evolution, relatively easy to pass. If life starts easily, then the statistical pressure shifts entirely to the future. A discovery of extant or fossilized extraterrestrial life would confirm that the universe is perhaps teeming with potential, making the great filter's location almost certainly ahead of us, confirming our worst fears about impending, universal self-destruction thresholds. Conversely, the absolute silence, maintained despite relentless observation across multiple electromagnetic spectra, subtly pushes the probability back toward the terrifying proposition that the emergence of anything complex is the near impossible step, yet this interpretation clashes violently with the known ubiquity of the necessary chemical precursors and planetary environments. Therefore, the synthesis of observational data and theoretical constraints leads to the most pessimistic, yet logically consistent, conclusion: either life emerges incredibly rarely, or technological life self-destructs reliably and quickly. Given the sheer number of potential starting points, the latter option, the self-destruction hypothesis embedded in the Great Filter concept, carries the heaviest weight of dread. The implication for current human endeavors, therefore, is an urgent mandate for existential risk mitigation. Efforts focused on planetary defense against external threats, asteroids, supervolcanoes, while prudent, address threats that are external and perhaps statistically rarer than the internal, self-inflicted threats posed by our own burgeoning capabilities. True survival hinges on mastering the constraints of wisdom, governance, and long-term resource management. The ability to solve climate change, to establish robust global biosecurity protocols that prevent pandemic-level releases of engineered organisms, and to rigorously address the AI alignment problem are not merely political or scientific challenges, they are the direct, immediate tests imposed by the silent verdict of the cosmos. Every failed negotiation over emissions, every major cybersecurity vulnerability exploited, every uncontrolled proliferation of biological research capabilities that bypasses international oversight, may represent a small stumble on the path toward the inevitable abyss that silenced everyone else. We are currently operating without a map across a minefield laid by the unknown laws of technological maturity. The absence of competing signals implies that the successful navigation time, L, must be extraordinarily long, spanning billions of years, allowing for galactic-scale expansion and colonization, which we are nowhere near achieving. If other civilizations had even a 1 million-year head start, they would have colonized or at least visibly permeated the entire galaxy by now, rendering the sky vibrant with their presence or the remnants of their engineering. Since the galaxy appears untouched, the implication is that L is drastically shorter than 1 million years for almost everyone. This leads to a final, somber thought experiment: what if the filter isn't instantaneous but a prolonged, slow decay? Perhaps the filter is the inability of a technologically complex civilization to maintain the intellectual curiosity or social cohesion necessary for massive, multi-generational projects like interstellar travel. As resources become scarcer due to local environmental mismanagement, or as complexity breeds incomprehensible bureaucracy, the drive to explore and expand wanes, leading to societal stagnation and eventual reversion or collapse back to a pre-technological state, effectively removing them from the detectable set L. The silence is then not a sudden explosive termination, but a slow fade into irrelevance, a failure to achieve escape velocity from their own gravity well, both physical and social. The universe offers no comfort, only immense data points represented by the void. Every astronomical discovery that reveals a new Earth-like world intensifies the paradox and sharpens the focus on our own fragility. We are the current incumbents in a potentially lethal cosmic competition, and the lack of competition is the most damning evidence we have that the finish line is universally impassable. The terrifying truth is that our success in observing the emptiness might be the final, fleeting moment before we, too, join the countless others whose final transmissions were never sent, their existence erased by the very power they sought to command. We are sailors on a dark sea, and the reason we see no lighthouses is that the sea itself is the lighthouse, its emptiness signaling the universal wreck.